All right, in this video we're going to look at a way to compute cross products. We're going to be calculating some cross products here. In the last video we talked about the definition, geometric definition of cross products as a directed area. And so if you use that to think about cross products though, or to calculate cross products, you would have to know that angle between the two vectors. And so that's usually not a very efficient way to calculate cross products, although in theory it would give you the same answer as what we're going to talk about today. So some textbooks start with what we're going to do right now as a definition of cross products and then show the geometric relationship. Our textbook starts with the geometric definition and then shows this relationship. Once we've talked about some properties of cross products, we'll prove that this works, that these are equivalent to the geometric definition. But this is what you want to use when you're going to actually calculate cross products. All right, so I'm going to introduce some notation that you may or may not have ever seen before, depending on your prior math classes. If you haven't, that's okay. It's not too hard to learn. All right, so we're going to talk about two vectors here. We're just going to call them V and W, or whatever they might be called. And we're going to calculate that cross product by calculating a determinant of a 3x3 matrix. So if you've never worked with matrices before, you might not have seen this notation before or know how to calculate a determinant, but it's really just multiplying and adding and subtracting, so it's very easy to calculate. So this particular 3x3 matrix, we're going to put across the top row of the matrix our three standard basis vectors for R3. So that is I, J, K. So you're just going to write those symbols, I, J, and K, across the top row of this matrix. That would be the top row. And then the second row of this matrix, you're going to put the components of your vector V. So that would be the three components in the direction of the x, y, and z axes for that vector V. So we've been using V1, V2, V3 for those. Sometimes people like to use Vx, Vy, Vz. V1, V2, and V3. And then on the third row of the matrix would be the components of the second vector in your cross product, W1, W2, and W3. So we're going to calculate the determinant of this matrix. So sometimes determinants are written using notation like this. They can also be written using notation that looks like absolute value bars. That's actually how our textbook writes the determinant. They don't write the DET out front, but instead of squared off brackets around the matrix, they'll put what looks like absolute value bars, which is another notation for determinant. It doesn't matter which way you do it. What matters is that you can do this calculation. So if you've done determinants of matrices before, then this calculation will be pretty easy. If you haven't, you'll learn it pretty quickly. It's not hard. So this is we're going to talk about this. I'm going to do some kind of waving my hands and then write down some formulas about this. So to calculate this determinant of a 3x3 matrix, we're going to do what's called expand along the top row. So you're always going to do it this way. If you've learned other ways to calculate determinants, this is what we're going to do and works well for cross products of two vectors. We're going to do what's called expanding along the top row. So for the I, first entry here, you want to think about eliminating the row and the column that the I is in. So you want to cover up with your hand or maybe draw a light line through. I'm not going to do that on the board here because that messes up everything, but cover up or ignore the row and the column that I is in. And so then what you'll be left with is a 2x2 part of the matrix here. And so we're going to do this cross product minus this cross product. All right, so for the I entry, we're going to take V2 times W3 minus this product, V3, W2. I tend to think about finding a cross product very mechanically in terms of multiply this way minus multiply that way. I tend not to think of it in terms of formulas, and I would encourage you probably to think about it more in terms of movement, very kinetically in this matrix here. All right, so that's for the I, and then I'm going to do the J as well. One important thing on determinants of matrices and cross products of vectors is that there is a plus minus plus relationship, though, in our determinant. So if you take linear algebra, you'll look at some other formulas for calculating determinants and why that plus minus plus is in there. But for right now, we're just going to use it for computational purposes. So for the I, we're just doing this minus that. And then we'll do minus plus minus plus relationship. So a plus minus plus. This is a common mistake, is that students will forget this minus here on the j component. OK, and then I'll eliminate the row and column that the j is in. And so I'm left with these two columns, v1 over w1 and v3 over w3. And so again, I'm going to do this product. So starting in my upper left corner to w3. So v1 w3 minus v3 w1. And that is your j. And then for the k, you're going to do the same thing. I'll just write that underneath here, but you can write it all the way across if you want. I just want to leave some space over here for an example. So for the k component, so plus minus plus. All right, and then for the k component, again, eliminate the row and the column that the k is in, and look at what you have left, and do this diagonal minus this diagonal. So you're always starting in the upper left corner, v1 w3 minus v2 w1, and that's times the k. All right, and so notice that this result is a vector. Remember when we talked about in the last vector, the geometric interpretation of a vector, it is a directed area. And so the direction is based on a vector. So remember when you do this, that you end up with an I and a j and a k. You end up with a vector. A common mistake is that students just leave off the I, j, k here and end up with a bunch of numbers, which doesn't make any sense in terms of thinking about what an actual cross product is. OK, so this can look a little bit overwhelming, but we'll just do a little quick example here and calculate a cross product and then talk a little bit about what that answer represents. OK, so I'm just going to write down a couple vectors that are pretty easy to work with. All right, so we're going to use 2, negative 3, 1 for our vector v. And for the vector w, I'm going to write this one in ijk form, j minus 2k. So whichever form your vectors are given in, you might want to switch them to the same form. I tend to prefer the brackets and commas so that I don't lose track of where things are at. This one is given to me in the ijk form. Notice that there's not an I just have a j minus 2k. I find it helpful to rewrite that sometimes in this component form. You want to put it 0 where the I component is since there's no I there. So 0, 1, negative 2. All right, and then I want to calculate the cross product of those two vectors. So I'm going to do v cross w. I'm going to set up a matrix like this, and then I'm going to do this calculation. All right, so v cross w is going to be the determinant of. So I'm using these bars that look like absolute value bars for determinant, or you can use this DET symbol. Across the top row, I'm just going to write I, j, k. No numbers there, just I, j, k. Those are the basis vectors. Second row is going to be the components of the first vector in my cross product. So 2, negative 3, 1. And then the bottom row is the components of the second vector in your cross product. So 0, 1, negative 2. All right, and then you're going to do all of this cross multiplying and subtracting like I was talking about over here. So I would not try to write down this formula. I would just try to do the cross products, the multiplications and the subtractions, and write down the results. So, all right, so in the I component, I'm going to have this product, negative 3 times negative 2, which is 6, minus this product, 1 times 1. So 6 minus 1. And as you get good at these, you'll just write down 5. I, that's in the I direction. And then remember the plus minus plus, the minus. That's a really common mistake. If you're getting wrong answers when you're calculating cross products, that's the very first thing I would check is, did you remember the minus on the j component there? All right, so in the j, I'm going to eliminate the row and column the j is in. I'll be left with this 2, 0, and 1, negative 2. So my product this way will be 2 times negative 2, so negative 4 minus, and then be careful here. This is a really common mistake, is that students multiply something times 0 and get something that's not 0, right? That answer should be 0. If you're multiplying by 0, you should get 0. But I often see Calc 3 students who I know how to do multiplication, mess that up, and then they get the wrong answer, and they can't quite figure out what they did wrong. So 1 times 0, that's 0. That's in my j component. And then in my k component, I'll eliminate the row and column. And so I get 2 times 1 is 2, minus negative 3 times 0 is 0. Okay. If I want to tidy that up a little bit, I can. 5i, or I can put this in bracket and comma form. Maybe I'll go back to that form. 5 in the I component, so 5. Here I have negative 4 minus 0 will be negative 4, but then don't forget this minus here. So minus negative 4, so that'll be positive 4, and then plus 2. All right, so this vector is what I get when I do the cross product of v cross w. So then one question might be, all right, so what is that? So remember in the last video we talked about the geometry of that's a directed area. So this vector 5, 4, 2 is perpendicular to both v and w. I could check that by verifying that the dot product that we did before, dot product of this vector with v is 0. And I could also check that the dot product of this vector with w is 0. So you can go ahead and calculate those dot products. 5, 4, 2 dot 2, negative 3, 1, and you should get 0, which again, remember from prior videos, that means those two vectors are orthogonal, which might mean that they're perpendicular. Since neither of the vectors is the 0 vector, we can conclude that a 0 dot product would mean perpendicular. And same here. So perpendicular, this vector is perpendicular to both of these two original vectors. Sometimes we want to do something like that when we need a perpendicular framework or for some other applications. And then the other thing is that the magnitude of this vector, so the magnitude of v cross w, which would be square root of 5 squared, 25, plus 4 squared, 16, plus 2 squared, 4. So square root of 45, or 3 square root of 5. That magnitude of that vector would represent the area of the parallelogram formed by these two vectors. So this cross product vector is a directed area. Direction, perpendicular, magnitude of this vector represents the area of that parallelogram formed by those other two vectors. All right, we'll do some more calculations with both cross products and dot products in some later videos. And so for right now, though, you just want to make sure you can practice calculating this and not make mistakes in the sign errors. Again, the math isn't hard here. There's a lot of things to be careful about with negative signs and zeros and things like that.